All right, so I'm going to start off with a couple of questions. Did anybody attend last month's meetup and see my lightning talk? We got one. All right, we have one. Our retention is one, which is, it's okay. Yeah, so for Pat, who I happen to know, the concepts that went over there are sort of like a prelude to some of the things that we're going to go over here. And the title of my talk is How to CQRS in Node. It's eventually consistent architectures that scale and grow, blah, blah, blah. One more question. Does anyone know, or is anyone familiar with CQRS? Okay, so yeah, so there's a few hands. So CQRS is a type of distributed architecture. All right, so it's a design pattern, but typically we talk about design patterns for things that happen within a single process, whether it's like the factory pattern for creating instances of things or an adapter pattern for wrapping an interface, stuff like that. CQRS is often described in ways that are really ambiguous because you have to kind of build up some blocks to make a distributed system. And so in order to explain this thing, you really have to kind of give like a high-level overview so people kind of get a little bit of an understanding of what it is, break it down into the different blocks, show how they're related, and then bring it back up and be like, okay, that thing that we just talked about for the last like 45 minutes, that's what CQRS is. And it's been kind of a tough thing to explain in the past. My goal for today is to make you guys walk out of here saying, I know what CQRS is, and that's cool, and I think I can do that. Sound good? All right, let's do it. So how to CQRS in Node, eventually consistent architectures that scale and grow. I could have just as easily left out CQRS and said how to create eventually consistent, distributed, unidirectional systems. But I didn't. It's 4 little letters is easier to do. So start off, who am I? I am a guy who's been coding for a long time. At one time, I was a .NET consultant. I was a principal consultant for this company called Magenic, and I got sort of a background in domain-driven design and things that kind of led me to these types of patterns. I went on to start a company. It was a Techstars company. We were in Seattle. We moved that company to New York. And when I was building that company, that's when I decided, hey, there's this thing called Node.js. Maybe I'll try that out and see if we can make things faster than we could in .NET. And anyway, I didn't want to hire .NET developers. So I tried it out, and turns out it was really easy to make these distributed systems. Today, we would use the word microservices to describe the components of this system, but back then, they're just services. But we had a goal of always making our services small, do one thing, and do one thing well, and that's what microservices should be. So that company was an online marketing company. It's called GoChime. I eventually left the company, did some consulting, but my co-founders did an amazing job, actually sold the company a month and a half ago. And the same software that we open sourced, that we built there and we open sourced, I went on to apply at a number of different companies. And it's turned out that it works in all sorts of different problem domains. And so it worked in an online marketing system that was churning through the Twitter fire hose in real time. And it even powers an electronic bond exchange, basically a stock market for bonds. $1.75 billion is traded over this thing. These tools allowed us to architect our system in a way that you could point different people at different services, say you own this thing, and then as your system grows, it's very easy to figure out where do we plug in some new functionality. So it's all open sourced, and other companies reach out to me too, letting me know that they're using these tools. We're actually creating a new site, and actually a tool called Microservice. Kind of a land grab of a name, but what are you going to do? And it's micro SVC. So in the next coming months, you're going to see something that takes all these ideas that we're showing now and makes it even easier to use. So let's dive into it. So that's me. Actually, that's me before I decided not to cut my hair for 7 months. So that actually is me. But so when do you CQRS? CQRS allows you to easily build real-time reactive systems. And this pattern has been around since before reactive was even a keyword or microservices was a keyword. So this is a pattern of ideas that we can apply to any new tech as it comes out. You use it when you want to prefer small modular services that do one thing well. You use it when you're building a system that you expect to grow over time. You're starting a new business. You're just discovering something about this problem domain. You're going to learn things. You're going to start up a new service. It's going to do something with orders or shipping or whatever, but it's going to do that one thing well. You're going to learn more, and you're going to add new functionality to your business, pop in a new service. It's super helpful in that it makes it really easy to organically grow your code base over time, such that when now your code is too big for one team, you can start splitting your teams easily, and it's very easy to subdivide the system out to the different individuals in your organization. It also stresses that every single different component in your system can be scaled differently. And we'll see what that means in a bit. For me personally, the answer for when do you not use CQRS is pretty small. Like, you're not going to use it for a static site. You're not going to use it for some CRUD application where you're just doing update, create, update, delete. But anything larger than that, I would recommend that you use CQRS, or you at least do sort of a halfway step. And if we have time at the end of the presentation, I'll show you how I did a halfway step to make the nycnode.com site. So here we go. So what is CQRS? Pump the brakes a little bit. Let's actually not say what CQRS is. That's the next slide. We're going to do a primer. So there's this dude named Bertrand Meyer. And in 1988, he was developing the Eiffel programming language, which I'm sure none of you use because no one uses it. It's totally academic. If you have ever used it, it was probably in a language concepts course in school. But it's pretty much like the reference implementation for object-oriented programming languages. And he came up with this this rule called command query separation that says, when you're designing objects, or the types that define objects, any particular method you're implementing should either be a command that performs an action and updates state, or it should tell you what the state is. Never the same thing. And you can understand why. Like, if telling something, or if asking for the state of something changed its state, you could never really know what the state is, right? So it's like a cat, the cat in the box. Once you touch it, it's changed. So that leads us to make these class diagrams like this. So you should always have your methods on some type of an object either do something or get something, and they should never do both, okay? So CQRS is sort of an expansion on that. You take that idea from the object level, expand it to an architectural level. And basically what it says is the externally facing subsystems, your APIs, your apps, they should get information from one location, queries, and they should update information by sending commands to another location, right? So your commands and your queries are coming and going to different places. Okay, so we'll talk more about how that actually happens, but that's the general thing. No longer are we updating and asking for the state from a single database. That's basically what that means. And so this is just sort of going over that last point, that by making that choice, saying that queries and commands go to different places, we're no longer going from one database. And that's going to have some implications that play out through our entire architecture just from that one decision. So what a CQRS looks like. This is basically the simplest example of a CQRS system that you can have. So we've got a web client served by a web app. We've got a backend microservice. We just call it service now, but we can pretend it's like an order service, right? So this is like Amazon v2 after they took it from a monolithic app and we're like, you know what, we're going to grow. So that's the order service. And you can imagine that the web client, when you click a button, it sends either a get or a post to the web app. In a normal monolithic app, this thing would just go and update something in a database and then immediately send back some response. But what we're going to do is go the other direction. We're going to send a command to the order service and say, order service, create an order. We're saying, update your state. He's going to emit an event when he's done. So he takes that event, updates his internal logic. Notice he has his own little database. That database only stores the data he cares about for his part of the system, and that's orders, right? So if this was like a MongoDB, it would literally have one collection in it. It's the orders collection. And when he's done, he emits an event. And that event goes over some sort of a transport, whether it's a queue or whatever, and some other process or any number of processes that care about that event, listen to it and say, someone's told me an order's been created, I want to do something now. And it's up to that service who receives it to determine what do they do. This is a special service, and we're going to sort of this is going to be a bit of a little mystery service, and we're going to talk about him a lot, this DNormalizer. We're going to spend a lot of time talking about how these services that sit below him are like an order service or a fulfillment service or a shipping service. And we're not going to exactly say what DNormalizer is, except that he listens for the events coming out of the other services and writes them to the horizontally scalable database in a way that's easiest for the UI to view. Okay, and so we'll get back to that. And so you can see that our command and the result of it end up making it back to our web client. And commands go to the services which emit events, and those are separate from where we do our queries. And because we made that decision, we don't read and write from a single DB. We just read from it. We now have a unidirectional flow through our architecture, and one that's eventually consistent. In the middle of one single nanosecond, at some point in time, the order services database is not going to be the same as the DNormalizer database, the one that our web application reads from. We just decide that's OK, because we're going to get a bunch of benefits from accepting a little bit of delay in time. Okay? And right now, there's one little event coming out over here, but you're going to see this pop up in a couple slides. That event that pops up as a result of a command, we call that the dance. And that has to do with what this distributed architecture is called over here. And we'll get to that. So what does a larger system look like? You might have multiple external-facing systems, and the unidirectional flow, this pattern, is going to end up looking about the same. An outside-facing application or an API will send commands to tell the system to update its state. The recipient of that command is whichever service handles that type of command. So this is the order service again. We're saying create order. He's going to actually create an order, store that in his local database. Transaction's now complete, and he's going to tell the world, my order has been created. He publishes an event. And now any number of services can listen to that. The DNormalizer listens to it because we want to update our horizontally scalable database and get that back to the web app, right? But there happens to be another service here that listens too. Maybe that's a fulfillment service. So he listens for when orders are created so that he can then dispatch them. Maybe he talks to UPS or the Postal Service or whatever, right? But that's his job, and he knows how to do that one thing well. And so this just sort of goes and plays on top of itself. Now, the web API can also make calls in. He may call some user account service. Maybe a partner has set up a new account. And so it goes and it does its logic, and then it emits some events, and so the other services care about that. The DNormalizer does, because he's going to update the horizontally scalable database, right? So our UI can read it, but the other services might care about that because they're going to use some user information when they process things like shipping, right? So it's a unidirectional flow. It's eventually consistent, and now we can see there's more than one event over here that's starting to comprise this thing called the dance. And what am I talking about when I say the dance? So we can see that as commands come into the system, into our domain, logic gets performed, and then events get emitted telling other services. This chain reaction happens, right? And so all of a sudden, this interesting, like, organic play of command causes a series of events from a number of different services begins to play out, right? There's an architectural design pattern that describes this, and it's called choreography. And the easiest way to describe a choreography is to say what it's not, which is an orchestration. So in a distributed system, if you have a broker in the middle whose job it is to handle a workflow and constantly tell it one step at a time, services do this, wait for a response, then tell the next service do this, and orchestrate those things such that some distributed workflow can be done, that's called an orchestration. The problem with that is you have a single point of failure, and you also have a single point of scalability issues when your system starts to grow. What CQRS uses is a choreography, which says, actually the decider of where events get published is within every single service. So imagine you're in Amazon, and Amazon just brought on some new team, which is like the drone shipping team. They want to know which new orders have been created such that they can ship them out. Instead of having to communicate with some team that does the central broker thing, they just spin up a new service, have it listen for orders. When the orders come into that service, it checks a property that says like drone equals true, and they know that they're the ones who are going to deliver that thing. And so it's super easy for them to get started. They know how to shoehorn their service into the system, and now it just organically scales out. And so the series of events that come after a command are this choreography, this dance. Okay? So we have a couple of different colors here for our lines. We have the yellow straight line and the yellow dotted line. Just as a quick little key, yellow lines mean messages. Their message is going over some sort of a transport, whether it's like RabbitMQ or Kafka for message queuing, something like that, right? The commands are, they're both messages, but commands are sent directly to processes, and commands tell a process what to do. And this is just sort of a nomenclature that we decide on, and it's going to help us build this system a lot more easily. So commands tell a service what to do. They're sent directly to a receiving service. It's usually from one service to a queue, and then that next service picks things up off the queue. They're sent fire and forget, and the language that describes them is usually present tense directive, so it's like order.create, right? Events tell the world that a service is done doing some action, and so the command came in, told it to do some action, the logic happened, things were saved to the database, we know we're 100% done, publish an event, and tell other services that you've completed these things, right? And so it's done in a broadcast fashion. And getting back to sort of like the nomenclature, we usually name these with past tense, because again, we're describing the fact that we just performed some logic in our service, okay? When talking about, any questions so far? Cool. So when you talk about a CQRS system, you know, we started with, this is like our second glance at what a larger CQRS system looks like. And remember, one of the things I said is, it's a bit of a big thing to understand what a CQRS system is, but what we're going to do is learn the ideas and the principles. So we start with this big view, and we're going to break it down, and then we're going to build it back up in our head so we understand it all. So when you're talking about a CQRS system, you typically have the front end and back end services. Front end services are user-facing, or maybe customer-facing, like third-party vendor. So they can be a web app that's feeding, you know, some JavaScript UI. They can be a web API that's feeding some mobile app, or they can be some sort of a third-party gateway that goes out to one of your client providers. And then you have back-end services. And these are the things that do what your business does, right? So if you have a bank, there's going to be some service that runs a ledger, things like that, okay? For now, we're going to start with that big picture. We're going to break it down, and we're going to start with the front end. So one of the questions is, what's different about a web application that exists in a CQRS architecture versus like a monolith that just talks to and writes to a database? Well, the first thing that's different is, although we still query the database to get the state, right? In a monolith, you still query the database. If you go and hit, you know, some meteor reference app, it's just going to say, hey, what's the current state of the database, and it shows it to you. Still the same. The difference is we don't directly modify that database. We get that database, we get the data from the database, and then once we want to modify the state, we tell someone else to modify it on our behalf. Okay? And the way that we do that is we send commands in the way that we just are explaining so far. And so apps expect that their read-only representation of the state will eventually make it around, right? So we talked about how it's unidirectional and eventually consistent. Client-facing apps trust that after they tell a back-end service to do something, that the result of that will make its way all the way back to the denormalized database. And one of the reasons they can trust that is because we tend to want to implement the commands and the events, these messages that are going between services using a reliable transport. So RabbitMQ, Kafka, ZeroMQ, et cetera, right? These are means of sending a message from one process to another such that, say, the process crashes or the process happened to be down for maintenance. When it comes back up, it'll immediately see that there's something on the queue and begin going again. So you know that even if some things may be turned off along the way, eventually when everything's running as normal, each step is sort of like transactionally complete and things make it all the way through the system. So let's pick a transport. And again, you can use Kafka, you know, any number of different transports. I build things on RabbitMQ because it's super reliable. So RabbitMQ is an open source messaging broker, and it allows you to do direct send between two processes using a queue. It also allows you to do broadcast or fan out and topic routing messaging, which means you use sort of like keywords to describe the different messages that are going out, and it will route them to the receiver. And so this is how we allow our processes to specify what events and commands they care about. Okay? Super highly performant, it's built in Erlang, it's open source. Honestly, like probably at least half of the major financial institutions in New York are running RabbitMQ somewhere. So it runs like exchanges. It's super powerful. Brew install RabbitMQ or whatever you do on your operating system. So let's pick a framework. So how are we going to use RabbitMQ from Node? Let's pick a minimalist framework and make sure that it's not some big unwieldy thing like Rails where you just want a piece of it but you get all of it. So I wrote, and this is actually one of the first things I ever wrote in Node when I was starting GoChime, and I wanted to make sure I could build these distributed systems. Service bus, it's super simple messaging in Node. It's basically the simplest API you can make on top of RabbitMQ. And by simplest, I don't mean like least lines of code. I mean to get it running in your process, that's where the least lines of code are. It supports all the different mechanisms that RabbitMQ does: direct send, pub sub, fan out, topic routing, etc. It's also used in financial exchange and online advertising, like I said at the beginning. We'll show some code in a little bit about just how easy it is to use. So again, what's different is what we're talking about right now for a client-facing app. And so the question is, how does this work? We've said that we read from the database, and instead of writing back to the database, we send some command to some outside service. So how does that work? Well, this is how it works. And this is the simplest usage that you can possibly do using Service Bus. You just require Service Bus, and you instantiate a bus. In this particular instance, since there's no options parameter being passed into the bus call, we're just saying use a expect there to be a RabbitMQ instance on localhost with all the default port and all that kind of stuff. And it will just automatically be ready to use as soon as you do bus.send. You don't need to do like bus.onConnected and register stuff. It will actually queue that internally so that if your RabbitMQ instance is slow to connect, as soon as it's all ready, it will all get flushed out. And I've never seen that become a problem because RabbitMQ is extremely fast at getting started up. And Node's extremely fast at initializing all this stuff. So what we have here is we instantiate our bus, and we're doing a bus.send call. So again, RabbitMQ has basically two different types of sending messages. It's direct from one process to another on a queue, or it's broadcast, fan out. And for the broadcast stuff, you can do some special routing. But for this case, we're sending our command from the web app directly to one service, and we'll call it the order service. Question? Yeah, so the question is, what does it mean for it to be reliable? How are the messages reliable? So RabbitMQ allows you to make durable queues and also have durable messages on the queues. So what happens is you can bring your processes up and down, but the queues will still exist, and they're persisted to disk. So what happens is unless those messages have been acknowledged, they remain on the queue. And so when this order service is done and it's saved to its local database, that's when he's going to say, ack this message. Bam, it's off the queue, you're done, and now you publish your messages, which we'll get to momentarily. So again, these are fire and forget. A bus.send takes a command name and then the command itself. And so it's going to use RabbitMQ to send a command via order.create. And then some service is going to determine, I care about order.create. And they're going to be the one to listen to it. And we'll get to that momentarily, how they do it. So once you send stuff, like this is pretty simple. Okay, like instead of updating a database via a Mongo update call, we did this thing. Well, then what? Then we wait. How long do we wait? Depends on how fast our eventually consistent distributed system is, but typically it's pretty quick. So we wait for our queries to bring us back the information that we need. And there's a bunch of different ways that we can get that information. If we have a reactive or a real-time system, what we'll find is as the message goes through that unidirectional flow and the DNormalizer saves it back into the database, if we're using something like Mongo, we're doing oplog tailing. So the moment that update comes in or an insert and that record changes in Mongo, it'll reactively automatically update our UI. So it's really cool to see these systems working where you know that things are going to these back-end processes and your front ends are just automatically updating. And to see them running in a test runner is even cooler. But CQRS doesn't really care what specific technology you use. That's up to you. So you could use Mongo, RethinkDB, you could do CouchDB streaming, you could do polling, GraphQL. It doesn't matter because this is an architectural pattern that guides how to put these things together, and it gives you the ability to choose at every little point what is best. And one thing to note is there's plenty of instances where product design solves this problem in a way that might sound outdated, but you come across it all the time. So the product design part here is you should send the customer to a thanks for processing your order, check back later for updates page, right? And then they come and they refresh, and maybe at some point they refresh and there's new data. One place where you've all seen that is through the Amazon.com ordering process. Before you submit your order, Amazon is going to tell you estimated tax, and it's also going to have a little asterisk next to it saying this is estimated, it may actually change. As soon as you do submit your order, you're taken to a page that says thank you, and then minutes later, your municipal tax and federal tax is all put together and comes to you in an email. And within some time, you can go and start checking your order pages. But clever product design helps you deal with different wait times between your processes. Most of the time, you're able to design things that are very quickly, but sometimes companies like Amazon, for instance, want to do a little bit of CYA. Like, they don't want their customers to have to demand that everything is already consistent and already known about the order process the moment they've hit the button. Most customers don't care. So again, we wait, and we're waiting for the back end, and we're waiting for the back end choreography to complete the dance that we talked about, because it's eventually consistent. So we talked about the front end. Any questions on that stuff so far? All right, cool. Let's talk about the back end. So this is what our back end looks like inside this little box. And so remember, we said that front end facing services send commands into the back end. The back end processes do some stuff, then they emit some events. Maybe that makes the back end processes do more. That eventually collects in this DNormalizer thing. Whatever that is, we're going to get to it. And that's what the back end is. But let's break that down even more. So let's talk about the perspective of a single service in the back end. What does he look like? What does he care about? And what does he do? So these 4 points are pretty much it. And let's pretend this is an order service again. So a backend service can listen for commands and subscribe to events. The listen and subscribe words basically mean listening for people to send me things via RabbitMQ, and subscribe is subscribing to broadcast or topic routed messages. They perform some business logic, so once they get that message, they're instructed. I've been instructed to create an order. So then this service goes and does the actual processing to make an order. That business logic lives inside his code base. And then when that's persisted and done, and it's updated its local state, it publishes its events and tells external services about the updated state. Any questions on that so far? All right, so what does that look like? Well, using Service Bus, this is pretty much the simplest representation of what you could make. And so this is basically a single-purpose microservice using Service Bus. We require our bus. Instead of doing the require Service Bus, I just put that in a different file, because you can actually do some configuration of Service Bus, give it some config and things like that. So we've made it into a little singleton that's reusable. And we have this function called create, and that's what does the business logic. We don't need to figure out what that is, but for Amazon, they've got some code that creates their orders. So Service Bus is going to listen for order.create, commands that are sent in from front ends. And then it's going to, and that's going to make it such that anytime a new command is pushed to the service over RabbitMQ, that command object is going to be available and this function is going to fire. We're able to then pass that to our create. The logic goes and saves things when it's done. If an error doesn't come back, then we can do bus.publish and we do order.created. And so now we've gone and we've informed the outside world of the fact that our service has successfully updated some internal state. Right? Notice that we're listening for commands. We perform the business logic like we said. And we also have these reject and ACK calls. These are important because, like we said, there's two scenarios here. We either create our order or we fail doing so. If we fail doing so, we still want to get that message off of the queue, so we don't have what's called a poison message. A poison message causes your application to crash. It then restarts, reattempts that message, and doesn't know how to get out of a loop of constantly doing that forever. And so we want to have some logic in here that says, well, if things do fail, maybe under certain circumstances, maybe it's failed for the 4th time, you just go ahead and reject that thing, get rid of it, log the error, and some humans know what to do. And then, of course, if we're successful, if we've been able to publish after doing all of our logic, we ACK it, it's off the queue. What this service needed to do is now transactionally complete. So we talked about how a service takes in a command that emits an event, and maybe some other services are are subscribing for those events, and they may then be motivated to do some internal work because they cared about the fact that an order was created. Right? An order created event was published from some previous service. So what does a downstream service look like? What's its perspective when it lives inside this backend distributed system? Well, it listens for commands and subscribes to events. It performs some business logic to process some commands. It updates local state. It publishes when it's done. It's pretty much the exact same thing as the first service. It just happened to not be the first one that was called in this particular line in the choreography, in the dance. Right? We're building up this system over time. And as the way that your system is built at first, perhaps only one service takes some command to do something because that's the intent of your system when you first built it. But over time, more services are going to be built that take different commands, and they end up dancing around and causing other services to take actions after you've published the event saying that the business logic was completed for that. Does that make sense? All right. So what does a sample downstream service look like? And again, this is the simplest possible one. So the only difference here is that we're using subscribe instead of listen. And remember, these are single-purpose microservices that we're building right here. And so the only purpose of this fulfillment service at the moment is to listen for order.created and do some fulfill logic. So this one just subscribes to order.created, which was emitted from our first service that was told to do something by a command. And it goes and it does its fulfill logic, and then again, it either rejects or acts after having published, right? So we saw the single-purpose microservices. How do you, say you don't want to have a system where every single action in your system has to have a new service that you deploy, and you have this giant mess. Amazon Lambda is an example of distributed systems that are completely functional. You have one function, right? Some people might argue that that ends up being really hard to maintain. If your entire system is just understanding what functions are listening for what messages at what time, you have this completely flat architecture with the number of files representing the number of actions that can happen in your system, it can start to get a little bit unwieldy. So some people might argue to have systems, or services, excuse me, where related events, related actions, and things that are related to domain concepts in your system all happen inside the umbrella of one service. And so that's to say, we decide that an order service handles everything that happens with orders. Or we decide that a fulfillment service does everything related to fulfillment. And we'll have the listens and the subscribes for the events that drive that business logic all sitting under the hood of one service. So how do you start putting these things together? Well, we could just do bus.subscribe and like list them all out, and that gets a little bit, that's a little bit rote. Instead, I've got a module called service bus register handlers, and this is just the smallest amount of convention that you can put such that you initialize this thing on startup and you give it some properties, you tell it where this folder is, and it'll automatically register modules that define handlers from within this folder. So what does that look like? So the first part was we initialize this little module at the beginning of our service. So we require our service bus instance here. We're getting it out of a little refactored module that we put it into so we can put config into it. And then we require service bus register handlers, and then we just execute that function and pass it the parameters that it needs. So it wants an initialized bus so that it can then go and figure out what subscribes and listens to do. We define some error handling, and that's important because we need to tell it how to avoid that poison message scenario. And we also want to be smart and have a unified way across our services of reporting errors, so that engineers, when errors do pop up, they know how to pinpoint this is where it happened, in what microservice, et cetera. And then we also tell it the folder path to our handlers. And so it'll know where to go and look for different modules that fit a certain format, and it will then load those up. And so what does a handler file look like? Well, a handler file has a number of different properties that can be implemented. There's a few more than this. But typically, you implement either a listen or a subscribe, which is the fourth one down. You can you tell RabbitMQ through register handlers what routing key to use. And so if you're using a listen with a routing key, that's saying that you're listening for the command of order.create. So just like we saw the listen for order.create a couple slides ago, this is basically that using service bus register handlers. Okay? We've also said ACK equals true. It means this is going to use a durable queue. And you can do some special things like naming the queue to make them easy to find when you're trying to debug things and stuff like that. But the really interesting thing is this bottom part where we have a callback now. Previously, remember, we had to call ACK or reject to deal with whether the message was popped off the queue and noted as a successful transaction or an unsuccessful one. So now we're dealing with that based on whether we just call CB by itself or whether we're passing back an error to it. And it'll go ahead and perform all that logging that we already described back in our last slide. Cool. Super simple installing this guy, npm install. But what about the work part? So a lot of times when people talk about CQRS, they also talk about event sourcing. And those things are like they're almost mistaken for one another, and that's one of the reasons why CQRS is a bit misunderstood. Event sourcing is often used with CQRS, but CQRS doesn't care how you save things in any particular service. The whole point of CQRS is such that every one of these services in this distributed system can determine, am I better off saving stuff to MongoDB or a graph database or a flat file, or do I just hold this stuff in memory because I actually get my data from some external source every time I load up? But it's up to the implementers of every service to do that in that service in the way that makes most sense there. There's no reason to choose one thing and to choose a hammer and use that hammer in every service when one service could be better made with something else. So some examples of this are, do you need an audit trail? Are you doing finance? Like, are you building a financial ledger where you're doing an append-only log as a representation of like someone's banking account? If so, use event sourcing. I actually have a framework for that called Sourced. Works great. Powers a bond exchange. Again, you could choose Mongoose for MongoDB. Typically, when I'm building these systems, I tend to choose Mongo. And I'll either use Sourced or I'll just use Mongoose. Everyone knows how to use Mongoose entities. The only time I ever use Sourced is when I need that sort of like audit trail of my models. So again, CQRS makes no assertions of this stuff. It's all up to you. And that's the power of CQRS. But wait, there's more. So it turns out that Service Bus also has middleware. So similar to how Express has middleware where an incoming request comes through and you can sort of set up different functions that can modify an incoming or an outgoing message object, you can do the same thing in Service Bus. So for instance, this bus.package middleware, which is included in Service Bus, will automatically wrap up whatever object you send it, put that as a data property on a new sort of memento object, and give you a bunch of helpful parameters on there with the date time it was sent, the service that sent it, and the type of message, etc. Correlate will automatically add a correlation ID. So that enables you to know when you're doing logging, you can log the correlation ID for the message that started some action within your system. So now you can begin to do distributed tracing around your entire system and see, someone clicked this button on a web application. We created a correlation ID that we're going to use to track that action. That caused a command to be sent to a service, which then caused a chain reaction, a choreography of 15 different events that happened, but the same correlation ID is used on all of them. And so we can use Loggly or whatever our distributed logging framework to put these all together and see exactly where something might have gone wrong if there was an error, or we can just see that things are going great. This retry middleware, which you can get from npm install service bus retry, that will actually modify the object and put a function on it and override the ACK and reject, such that it will make your service, if you fail and you throw an exception and you haven't rejected a message, it'll retry it 3 times. And then after the 3rd time, if it's still failing, it'll put it onto an error queue for people to look at. And so the purpose of that is, one, that helps you get rid of that poison message scenario. And it also sort of takes into account the fact that there's always going to be errors. And you need to have some mechanism in your system for humans to know when to come and look at that error, see what caused the error, and then correlate that with some logs. And so using service bus retry, and having some good error handling in your service bus register handlers definition puts those things together. But wait, there's even more. So we said that you can do the bus.correlate, and that puts a correlation ID. Turns out there's also service bus trace, which is a utility that takes those correlation IDs, publishes them to Redis, and now you have a utility that you can use to, in real time, see your message flows using the correlation ID, go through your entire system and debug it. I'm working on a front-end UI, so this can all be done and looked at from the web. But right now, there's this fun little CLI app. So recapping on back-end services. We talked about how from front-end facing services, commands come in. The back-end services process information. They save it. Once it's transactionally complete on the inside, they pop the message off the queue by calling ACK. They then publish an event telling the world that they are done with their activity, and then some downstream service gets it, and that gets repeated ad infinitum. So service 2 takes over from service 1, does its logic, et cetera, and all these publishes of events end up coalescing at this DNormalizer, which saves them into this DNormalizer database, which is what updates your user interface. And so the backend services, from their little world perspective of just existing by themselves, they listen for commands, subscribe to events, like we said. But at the very beginning, I said that we were going to talk about this DNormalizer thing, and it's going to be this mystery. And at some point, we're just going to be wondering, like, what is that thing, right? So it turns out that the DNormalizer is just another backend service. So just like every other backend service, it either listens to or subscribes to events. The DNormalizer happens to just never listen for commands because it doesn't have any real business logic. Its sole responsibility is to listen for all the different events that describe things that happened in other services, and then write some denormalized UI-specific format of that event so that it can update the UI. And so that's to say that the way that you save your order in your order service might not be the most efficient way to display it on your user interface. Maybe it's got 25 different properties and a bunch of relationships to different things. And on your user interface, you just have an order ID and someone's name and a list of product names, right? So the denormalizer's job is take the event that was published out of some service and save just the pieces that we care about, such that it automatically will now update the user interface. Does that make sense? Cool. And so the denormalizer is sort of this key that completes our unidirectional, eventually consistent system, so that we read from our read-only database to begin with, and instead of updating that database, we told a service who's responsible for some part of our business to do something. It did its thing. It told other services about it. The denormalizer listened to it, and now we've got our information back to the user interface so that the user can see that it was completed. And a denormalizer ends up looking kind of like this. There's all these different handlers from service bus register handlers that are on order, cancel, created, modified, and they're just, in the systems that I build, it's typically like a Mongo database, and they're just doing upserts. So there's an order ID for these order, cancel, created, and modifieds, and they'll come in, and whichever one was last and has a larger version number is going to overwrite, and boom, your front end is automatically updated as a result of the dance, the choreography of events. So, recapping the big picture, this is the same thing we started with. Client-facing and outward-facing services send commands. Services accept those commands, perform some internal logic, publish when they're done. The same thing happens as a result of that in additional downstream services. Eventually, those coalesce at the denormalizer. We can now query for the updated data. If it's real-time, we're using oplog tailing or whatever, it automatically gets there. Otherwise, we design a product so people just hit refresh or come back later or click a link from an email. It's unidirectional. You can have as many different outward-facing apps firing into the domain as you want. There's this dance. One thing to note also, a common question is, does there have to be one denormalizer? No, there doesn't. You could have one denormalizer per outward-facing application if you wanted to. The thing to keep in mind is that these messages are going to be multiplied, and so as you have more denormalizers, if they're listening for the same messages, you may be doubling the amount of messages that are going through your entire system. So the better way to do it is to have one denormalizer and make it horizontally scalable. And so one thing I've noted is that CQRS allows you to make important decisions about processes at the point of every single process. And notice that some of these different processes have single boxes and some of them have multiple. So because we have this loose coupling between all our systems, we've said we're going to horizontally scale our order service. We're not going to horizontally scale our denormalizer, but we could if we wanted to. And so it allows us to make the decision at every different point to have this extremely malleable system. And when we onboard a new system, a new little green rectangle comes in here, it subscribes to events, new dotted lines go to it automatically. It can emit some new stuff. We update our denormalizer to take its events in once we have gone through QA and we know that the service is doing what it's supposed to. Now those get back into the denormalizer DB, and they make it to the front end. So hopefully, if you guys come across some conversation, people will say something along the lines of like, CQRS, I have no idea what that means. I think it was made up. Hopefully that myth is busted for you guys now. So thanks. Any questions? Cool. It's typical. So the question is it an anti-pattern for the denormalizer to publish? And yes, it is. And the reason is you don't want the denormalizer to have any domain logic, because once it has domain logic, that domain logic should actually be in a service of its own. And it should be in one service that knows how to do that one thing well. All of these things are principles and not laws. So maybe there's some point when you're building your system where you're like, you know what, like we really need to build this this like monitoring service so that every time an order gets created, we actually go and write to this other thing or tell this other service what to do. You can always choose to do an intermediary step and be like, you know what, for now, we're going to shove this code in the denormalizer. It's going to publish, it's going to republish something, and we know that we're going to mark it as some code that needs to be revisited later. It's always up to you. So these systems, you don't have to just build a 100% reference CQRS system. You can take these concepts and apply them to something you're building, and they can still be beneficial even if you're not 100% CQRS. Cool. Yep. Yep. It does. Yeah, no, it's persisted, yeah. It's persisted because you want it to be durable itself. If the backend services go down and aren't working, you still want the system to represent its last known state. Right? And then as other things come back online, those messages that are on queues begin getting processed by the different services. They begin publishing again, things make it back to the denormalizer, and now your data is coming back to you in real time.
And the actual data that comprise the denormalized version of those data, they store per service.
That's right. Yeah, so the question is, where is the true golden copy of the data? And the true golden copy of the data is living in smaller, more manageable databases that are paired up with each individual service. So one team can be responsible for things, for the data regarding orders being created. Another team is responsible for the data regarding shipping. And you end up avoiding having this huge monolith of code where teams are stepping on each other. A change to one piece of code causes another team to have to like deal with change control. It's totally loosely coupled. Yeah, so that's not really how RabbitMQ works. You can have a confederation or like a cluster. So the question is, what happens when I add more RabbitMQ servers? What happens when I need to scale this? What happens when like my business is making money, so I want to start making this thing bigger? Yeah, more subscribers. How do you satisfy having more services and more throughput through your system? So you do have to scale up RabbitMQ. Again, you can choose Kafka, you can choose ZeroMQ, whatever you want to do. For the RabbitMQ implementation, you can have a cluster, and they act in unison. And so you actually end up having sort of like a virtual instance name on RabbitMQ, and those define sort of like separate domains through which all the messages flow. So you can scale up to 5 RabbitMQ servers and still not get redundant messages sent. It manages that for you. It'll distribute the connections and the subscriptions across the instances for you. Okay. Yep.
I think, were you asking how you prevent a service that's been scaled horizontally? Let's say you have 3 instances of this
Got it.
service. How
Yep.
do you prevent them each from hearing, oh, there's been an order created, and then
Is that the question?
all 3 of those guys send
Okay. Okay, so many instances of the same service. Okay, right. So I answered about multiple RabbitMQs. What happens if you want to scale your service horizontally, right? So that order service, we had like 16 different little green boxes stacking up diagonally. What you need to do is figure out how to shard your data. So for instance, when we built Electronify, we built a corporate bond exchange. You can't have all of your bonds being processed by one single process. It's just like you can't scale a box that big, right? Same thing with a stock exchange. There are so many different stocks, you can't have the trading engine for a stock exchange all in a single process. So you need to scale them. So what you end up doing is you have to be creative with the command and the event names, such that you use sort of that naming pattern of order.create, but maybe what you actually do is order.identifier.create. And so now what you can do is you can use the topic routing capabilities of RabbitMQ to say when a service starts, it asks some other service, I am number 1 of 16. What are my subscriptions? And it gets back an array of strings. It then loops through those strings, subscribes to them all, and now 16 out of 5,000 different stocks or bonds or whatever, those orders are now routed to that process. All right, so what you're effectively doing is sharding, right? And if you have that problem, it's probably a good problem to have, right? Because people are using your system. Yep.
I have a question about the command names and the event names.
Yeah.
Are those all like well defined ahead of time, or do those get made available to RabbitMQ who tells everyone, hey, now this new service is here? Yeah, just curious about that.
Yeah, so there's no, so the question is, how do different services find out about what topics are available? What commands exist in the system? What events can be published? There's no central list of these things. What happens is RabbitMQ doesn't care what you tell it to send. It will take the parameters that you give it about how it will send something, and it will just do it. And so if you use service bus and do bus.send, there's some code behind the scenes that says, hey, RabbitMQ, assert that this queue exists, and then it just says fire off to that thing. Now, if I had a front-end application and it was firing off cornucopia.create, and I don't have a cornucopia server yet, it'll still tell RabbitMQ to fire off that message, and it will just dead letter it. It dies. So the actual list exists in your code base. It's distributed out amongst all of your different processes. And if you're using service bus register handlers, it's super easy for engineers to figure out how to find it, because you just look in the handlers folder. And you look at the names of the file names, which you should typically name after the different events or commands that they're listening or subscribing to. Does that make sense?
So you're talking about like not a ton of event names. I mean, it's pretty well-defined set.
No, I've had systems that have had like 16,000 event names. Yep, because of sharding. Yeah, you end up having commands that are named after, like literally at Electronify, we had, so the difference between stocks and bonds is that stocks, there's like, I don't know, a few hundred or a few thousand of them, because every company can have one stock. For bonds, companies can issue as many bonds as they want, right? So a company could have 100 different bonds. So the sharding problem for building a bond exchange is actually much harder than the sharding problem for building a stock exchange. So we had different command and event identifiers for every single bond that exists. Yep. Any other questions? Yep. Yeah, the read's easy. It's the exact same Mongoose call that you would use to read from Mongo if you happen to be using Mongo. If you're using GraphQL, it's the exact same. It doesn't change. The only difference is we're just not updating those databases directly from the same process. We took that update call and moved it somewhere else in his own little database, and then he publishes something, and then a similar update call happens in the DNormalizer to update the corresponding location that we're going to end up looking at in the outward-facing application. Does that make sense? It's a bit of a duplication, but it's not duplication meaning you're doubling your effort. It's duplication in that we acknowledge that the way that we want to manipulate our data in a background service might be different than how we display it. So although those things may have the same names, like maybe there is a order record in the database for the order service, and there's also an order record in the denormalized DB, the properties on those can look totally different. An order record in the order database that might only have one order collection in it, there might be no other collections, could be some big, huge nested document with a bunch of information about that order. And then the order record in the read-only DB could literally just be the order ID, the user ID, and then some read information like the person's written name, or the product name, or a list of product names, et cetera. Does that make sense? So although the names are the same, we're saying that the concept of an order in the order service can be different from the concept of an order in the denormalizer. And further, since we said that these downstream services listen to events and they can do their own thing, there can also be a different concept of an order in the fulfillment service that just has maybe no readable information and only identifiers in it, because it's just a machine using that to do some sort of some business logic. Does that make sense? The read's not an event. The read's the same thing that it would have been. So we still read data from the same place using the same mechanisms. We're just moving some of our data to a different part of the architecture. But you're still just using a mongoose call. You're just saying mongoose.model.orders.find in your web application. That actually doesn't change. You just get the information. But you understand that when you update it, you're not doing a mongoose.models.orders.update. Instead, you do a bus.send. And we understand that the eventual consistency in this unidirectional flow is going to cause the denormalizer to update the record that I'm expecting to update. Make sense? Cool. Yep. We'll take one more, and then if there's extra time, I can show a little bit of extra stuff. What's up?
So a quick one. Like when you're doing like you can use sockets and do like push event at the end, but if
Yep.
you're just using like request response,
Yeah.
the way to do it would be to make like a promise in your like response handler.
Yep.
And emit event, and then resolve once you've gotten the like result of event.
And typically, yeah. So the question is, okay, say you do want to have an immediate as possible response from a back-end service to a front-end service without having to go all the way through the denormalizer. Is that possible? Should you do that? Just like we were saying over here, these are principles. You can violate them if you feel like it, and if you feel like you should. And this is one of the times when people sometimes violate the principle and say, actually, I want to know right away. So for instance, for some people choose to do authorization with this because you want to know right away. You don't want to wait for some denormalizer thing to update and then you know if someone's logged in. For that, you use RPC, and it's basically what you just described. So RPC means you make a request and you set up some listener for someone to then publish an event to you, right? And so for this example, we would have an authorization service, and you would send it a login request command. It's going to go and do the bcrypt stuff that that auth services do. It's going to determine if this person actually should be logged in, and if so, they publish an event. And this is a case where actually the front end subscribes. And the only additional thing that needs to be in there is a correlation ID, because you need to know that you're serving so many requests per second, there could be a number of different promises. When this new thing comes in asynchronously, your thread or your event loop is already gone, that's already ticked. So you need to be able to look up, based on a correlation ID, does that promise even exist? If it does, well, now we can go ahead and fulfill that promise, and guess what? You're online now. Does that make sense? Cool. So I was expecting someone to ask the question, is it okay to partially do CQRS? And, or if you have an existing solution, is there a way to make it a little bit more CQRS and step your way to it? So I know we're getting a little bit late on time. It's 9, but I can use 10 minutes to show you how I did exactly that to make the nycnode.com site if you guys want to see it. You guys want to see it? All right. Cool. All right. So NYC Node. So thanks to the work of Pat Scott, sitting right here, who is a DevOps wizard. He showed me how to take all this stuff and use Docker and totally Dockerize all these containers. So guess what? You can also do CQRS and containers and have it totally composable that way. Cool. So we're going to restart Docker. OK. So while that's happening and Docker is restarting, let's walk through the code. So what I have here is sort of a, in the pretty soon time frame, my talk from last month is going to be online, and you'll be able to go and watch it and see how I make meta repos of additional repos using this thing called git slave. But this is a repository, this entire thing. And these are actually sub-repositories. And there's a tool that knows how to keep them all in line together, so you can do like git branch on like 50 repositories at once and have like unified code pushes. So that's what this is. This is my meta repo. And I've built up these different microservices using a quasi-CQRS pattern to power this node site. And the node site is one that I just found and forked online of a Keystone.js app. So I wanted to be able to spin up these different services that did stuff as I added new functionality to our site. And I didn't want to have to navigate Keystone.js, one, because I didn't really know it until I built this thing. Now I feel like I do know it. But even then, I don't want to have to shoehorn in things like cron processes that are checking for new data on Meetup via the Meetup API. I don't want that to exist inside of a website. And so I want them to be these different microservices that live on their own. I can scale them on their own. I can shut them down if they're broken, stuff like that. So how did I go about doing that? So there's no place in NYC node-site yet where I'm publishing events or sending commands. So I have sort of a quasi-CQRS situation here. What I have instead are these apps that, that start up and reach out to the outside. They all have these schedulers, and they're scheduling some sort of cron job, and there's some sort of a thing that they're doing. Now this one runs on a schedule, and every 15 minutes it checks to see, has Matt created a new meetup? And so it checks the Meetup API. If new data comes back that wasn't there before, it publishes an event and says, new meetups found, and it gives the array of meetups that exist. Those then go into, those are then taken up by the DNormalizer, which updates the, quote, scalable, read-only, horizontally scalable MongoDB, which is just the DB that Keystone.js was using, right? Now, what happens is, and we'll just walk through this, I've got this import meetups. There's a couple of steps that it does. It fetches them. This is it going out and knowing how to go to the Meetup API. And then it publishes them. So when it publishes, again, we have publish meetup.found, right? So this is the thing in my domain, a meetup. This is the verb. It was found. And we passed the array of meetups. And so now what happens is automatically, since we use service bus register handlers to register these handlers over here in the DNormalizer, he has this meetup.found handler. And so he's listening for all those events. Those are going to be routed to him from RabbitMQ. He's going to log some stuff just so I can see it in the logs. And then it's going to go through. And although the shape of what Keystone knows to be a meetup is different than what Meetup thought was a meetup, because Meetup had all these extra properties, I shaved that down and I saved just what Keystone.js cares about, right? And so I'm using Mongoose, and the way that the models are done actually look a little bit different. The Keystone.js model that wraps Mongoose has a bunch of extra properties on it. This one's just what we need. So what happens is the array comes in, this thing loops through all of them. It does an upsert, actually. It's not an update. So I can run this as many times as I want, and if my data goes bad for some reason, I can come back, make my code change, run a command that will either do this automatically or I just wait for cron to run it again. It's going to go back out to meetup, find all the meetups, send them back to the denormalizer. The denormalizer is going to upsert them all, and bam, my site now automatically has all of the data in it. Same thing goes for users and videos found. We can see that this is the exact same thing, async.map. It's going through all the different videos. It's saving them with all the, like the YouTube external ID so that I know where to direct the iframe. That allows us to play the videos. And if we go back and we look at the YouTube ingester, it's almost the exact same thing. So our scheduler is just scheduling this import videos, which is going to go and it knows how to fetch things from YouTube. It's actually just saying what videos exist in a playlist that I made on the NYC node account, and it gets all of them. It publishes all of them. Those go to the denormalizer, and bam, I've just reconstituted my entire database. And that happens on a schedule, and so at any point, if my server crashes, I just git clone this thing, pull it all in, I do docker compose build and up, and wait 5 minutes, and I have reconstituted the entire NYC node database and site. And so there's no place in here where I'm using commands to tell services to do things. So it's a quasi-CQRS system. But as soon as I start deciding that I want some business logic that lives inside of NYC node, if there's stuff that we do that we can't just get from YouTube or from Meetup, if we're collecting comments from you all, if we want to add the ability so that people can make blog posts and have them saved, then we'll start making it so that Keystone.js sends commands to a blog post service or something like that. And those things are stored in a way that consolidates the logic for that in one little service, makes it back to the denormalizer by publishing, and then updates the read-only DB. Does that make sense? Cool. I don't know what's up with Docker. Let's try it again. It says it restarted. Boop-a-doo. All right, well, I'll figure out how to get Docker working here in a few minutes if anybody has extra questions. What's that? Yeah, wait, it's coming up. All right, wait 1 second. Here we go. So we're going to hop over here to our website. So this is Service Bus again. This is the thing that we've been talking about. This is Service Bus register handlers. Service Bus retry is the thing that we said will automatically change our service's behavior to retry 3 times, then move messages to an error queue. Service Bus trace was that thing that allows us to use the correlation IDs and see real-time tracing of our systems. And of course, we're about to see how we did this over here locally. 1 second. So things are bouncing a little bit. OK, cool. So what happened there is things were bouncing because RabbitMQ was coming online. So services were trying to start. Service Bus was throwing an error because RabbitMQ wasn't online. But eventually, the system healed itself. Right? So now we've got Redis for caching and RabbitMQ all set up. And we've got a number of different services that are running. So if I come over here and I look, now we have a working site. Hang on 1 second. Hey, Pat, what's the command to tell it to get rid of its data? That's it? Cool. OK. So this should load back up pretty quickly. And we should have a totally blank site. And then what we're going to do is I'm going to send a couple of commands to the Docker containers. And you're going to see that within a couple of seconds of it coming back online, we have a site that has all the same data as the currently completely live NYC node site. So building the denormalizer. Any other questions while we're waiting for this to happen? Sure. AMQP. Yeah, Service Bus doesn't have a pluggable capability for that, but there's no reason you have to use Service Bus to do CQRS. Although I did actually go ahead and do half the work. You don't have to use RabbitMQ, right? Yeah. Yeah. Oh, sorry. Right. What I'm also saying is that right now, Service Bus is tightly coupled to RabbitMQ. However, I've done half the work to make that decoupling so that you could use other providers. So that might be coming soon. OK, so we are back up and currently cycling, waiting for RabbitMQ. And now it's actually doing a bunch of stuff. So I need to try and refresh this fast. OK, cool. So we just deployed a new site. Go add some data. It's actually adding the data right now. So it already went and ingested a bunch of, let's see, actually, nope, that's just building indexes. OK, so right now there's nothing, right? We don't even have the top of the site. The site doesn't know how to function because there's no starter data in it. We need to add a meetup, and we need to add some videos and stuff. So what we can do over here, oh, it's actually started. It looks like it's pulling in all the users right now. So in a couple of seconds, you're going to have a user on my local machine. So first, I think we only have one meetup in here right now because it just got the current one. So let's backfill it. So we'll go and say backfill. So we can see that now it has, so the meetup ingester didn't log it, but the DNormalizer has denormalized 67 meetups. So bam. Now we have all of our meetups. We just reconstituted all of our data. And we should be able to do the same thing with the YouTube ingester. So there we go. What happened here? That's some sort of a strange... oh, I think they're probably, I needed to specify an environment variable. But yeah, so I need to figure out, or I need to add an environment variable to the video ingester. But it would have done the same thing and gone and grabbed videos and basically made it look like this. But so that's how you can take an existing project. This Keystone.js project was my thing, and use parts of CQRS to make a system that's more easily manageable and expandable, because all the business logic ends up living in these microservices, and it's up to you to pair up which microservices react off of what things just based off the events you're publishing. And then, of course, the DNormalizer updates your read-only UI. And that's it. Yeah.